This case study concerns the project Lakeshore Bristol. It's located in the UK on the southwest coast near Cardiff. Commissioned in 1967 by Imperial Tobacco, this building was with an architecture inspired by Mies van der Rohe with outside skeleton of Corten steel. In 2003, the site was redeveloped to apartments by Urban Splash, and it includes a ground source heat pump system and a biomass boiler. It won the Housing Design Award in 2007 and has a very high BREEAM rating because it's a very energy efficient building. So on the right here, we can see an artist impression of the actual site. It already had a vertical borehole heat exchanger installed, but due to, amongst others, the economic crisis, redevelopment was halted between 2007 and 2008. When it was restarted by Urban Splash, actually the energy demand of the building was unknown, and also the design of the ground heat exchanger that was installed was unknown. Groen-Holland was appointed to retro-engineer the design and deliver a ground source heat pump system that could fit the existing borehole field and still deliver a significant amount of energy to the building. The first step in the process was to do a detailed energy demand calculation based on a dynamic simulation with the Transys program. In total, there are 286 apartments ranging between 30 and 115 square meters, distributed over 7 different levels. Now, normally you don't simulate all the apartments. You look at apartment types based on the level that they are, the exposition that they have, if they are in the middle or on the corner, what is the surface area, etc. So at the end of the day, we had 67 different apartment types defined for 4 different zones using ambient climatic conditions from a nearby climatic station in Cardiff. So the results of these calculations, here on the right you can see the energy demand curve. There's a little error there, it says temperature, but it should read capacity. We can see that we have about a total of 830 megawatt hours of heating load. Additionally, 610 megawatt hours of domestic hot water demand. So a total energy demand of 1440 megawatt hours with a maximum capacity of 550 kilowatts. At the same time, we can see, if we analyze the frequency analysis of the hourly loads, that about 90% of the energy can be delivered with 350 kilowatt capacity, which is, of course, significantly less than the 550 kilowatt. Now, using this information, we started to, let's say, retro-engineer the borehole field. And the question was, how much energy and peak capacity can the borehole field sustain? We looked at all kinds of different scenarios with and without additional regeneration. Finally, a scenario was selected where we could deliver around 750 megawatt hours of heating, so about half of the total heat demand, with 200 megawatt hours of regeneration included, regeneration due to solar panels. The plant was constructed and delivered to site. You can see in the schematic that we have a heating-only system with a heating buffer connected to the building with a plate heat exchanger and a solar panel array used for regeneration. The actual plant looks like this with 2 4-compressor heat pumps. So each heat pump has 4 compressors in total. The total system is 8 compressors. They're all on-off compressors. So we have a fairly good match with part load conditions. On the right, you can see, the whole system was built on skids in Amsterdam and delivered to site on a lorry. It's been running well since it was installed, and if you want to know more about it, there is a paper published in the RevHaus Journal 48 in 2011.